Hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. We are going to finish SIMD optimizing the lighting today, and that'll be nice because we don't even know how well we did yet. We haven't even seen how much SIMD optimization will help us. We're totally in the dark about that actually, and as someone pointed out on the stream just now, also I don't think we've ever re-enabled multi-threading with the SIMD code yet either, right? If I'm not mistaken, yeah, that's still turned off. So we don't really know anything about what this will look like when we run it. Right now, it is, I believe, slower than the non-SIMD version. I would assume because we still downshift to a loop on the interior, but I guess I don't really know if that's the case since we never ran it the other way. So what I could do is run it multi-threaded now and see what our status is, since that's what people were wondering about. I agree that's an interesting data point as we finish here, just to see what the difference would be. So running in O2, if we take a look here, what we've got, oh, someone's angry. What is the problem? Compute light propagation. So it looks like box surface index is coming back. Well, I guess we don't really know what it's coming back as because this is in O2 mode. So in O2 mode, we're getting a weird result there. Let's take a look at that. So what happens here, right, is for box surface index, we are actually talking about the thing that's returned from the Ray code, which is not the same as in that case. I mean, it is the same meaning, but it's not a loop. It's actually something that just determines, that's like reporting back here which one it is. So box surface index here is something that comes out of the Ray results. So it's this thing here where we've got Ray bracket 4. The box surface index is accessed off of the individual one we're looking at here. And when we find that we've got a hit, which is determined by this getBox call here. Oh, so there we go. So this box index, this is a problem here. So we're not actually, this won't necessarily return 0 for 0, I don't think. Because box 0 is not a reserved box, I don't think. We probably want it to be, would be my guess. And we probably want that to be clear. So if we take a look in here, right, this is always going to return a valid box because box 0 is going to be valid. So, you know, I don't know how exactly we want to do this. It's a good question. We'll have to play with it a little bit, but let me just go ahead and insert a value there temporarily so that we have a clear way to do that. So in here where that's not where we want to be. I always start talking before I actually get to the place because that's just easier to have the flow of the narration of the stream. So it's like sometimes I'm on the totally wrong file and I'm like, here in the thing, and it's like, well, no, we're not here in that thing yet. That's where I want to go. It's not where we're there yet. So here in the file where we define the results, if I go ahead and put a B32 in here that's just like hit or whatever, right? Then what we can do is when we're actually checking this, when we come through and set it, right? Then we can just set all of these hit values here. And we'll play around with how we want to track that when we undo this loop down here. We still got this one loop down here, right? Right here. We still got this one loop right here that we got to get rid of. Today, when we get rid of that loop, that's a good time to figure out how we want to broadcast the results of the hit back to this routine, because that'll tell us what's going on, right? So in here, really all we have to do, we're looping over the subrays. What we can do here is just get rid of all of this stuff pretty quickly. We can just say like, all right, I think box surface index and the Ray position here, those are both inside this, right? So, in fact, even this is. So really all we have to do here is just do this. If ray subray, oops, hit, and then we know we can just rely on in here, if this is true, we just have result C index hit equals true. Now probably what we'll do instead is just report back the mask, so we don't have to do any work, right? And then the outside code will be the thing that actually looks for the mask or something, right? So you can see that this will, we're just doing this as a temporary plumbing procedure, and we'll get rid of it in a second when we actually clean that up, right? So, all right, let's take a look at what happens here in the O2 version. Here's the O2 version. And so, what the? So I guess that bug, which would have been happening all the time, was a pretty big one, right? Because now we're running at 30 milliseconds, but I don't think we're doing any less work. Did I enable the... So just that looked like that must... Oh, no, okay, there we go. I was like, I must have enabled... So let's do that again. I was like, I must have enabled the multi-threading, and I had. I just forgot I had. So, okay, so here's the single-threaded SIMD version running here, right? So there we go. And this is doing, again, this is doing, I think, all 64 arrays, right? So this is 16 casts of 4 arrays each. This is the full 64. So when we turn on the multi-threading, oops. This is the full version that we were trying to run at speed before. And now with SIMD, it actually is running at 30 frames a second, which is not as good as 60 frames a second, but it's getting there, right? So, you know, we're making improvements here. We've still got a lot more work to do. So I think we'll get a lot faster than this eventually. And I think we'll also be able to reduce some of the flicker further, because there are some things I hadn't tried yet regarding flicker as well. So, you know, we're definitely getting there on lighting. And we're still retaining a lot of the kind of fancy features that I didn't want to get rid of, so that as we sort of use this lighting more in the actual game, we can have cool stuff. Like, I like the fact that we still have subtle bounce, like blue light that bounces off of surfaces and red light that bounces off surfaces and so on. I just kind of like that. And so I think as we improve the lighting, which we will do, like, that's just really nice. I mean, I don't know. I think it's pretty cool when you get into when you get a light near a wall and it produces that bounce color. I don't know. It just feels really good, and kind of brings the game alive in an interesting way. So yeah, I'm pretty excited about the potential of this going forwards as we clean it up and improve it. And you know, I just think it's going to be pretty interesting. And we still don't really know exactly how we're going to use the lighting at render time either. So, you know, right now, I mean, that just looks good. Even right now, that in there, that lighting just looks kind of good. But we haven't even done a bunch of stuff that we want to do that, you know, we could do during render to maybe smooth it out and make it more continuous across continuous surfaces and stuff like that, so that we can have both the sort of nice articulation that these are blocks, which we're getting, but also a little more coherency in the light when there shouldn't be breaks, which we can play with. And again, I don't know if we actually want that. It may turn out that the art style really wants it to be discontinuous across blocks, but, you know. Anyway, so looking good, but we've got work to do. Let's go ahead and finish. But I'm happy that we're at 30 frames a second already. That's kind of a nice turn. So if we come through here and we take a look at our raycaster, I'm going to move it to the other side so that my head is not taking up part of our code view there. So if we take a look at what's going on in here, I'm going to go ahead and take this code out now that I'm pretty sure we're doing a reasonable job of that. So if we take a look through here, we can see that we get down to this part of the loop, and this is where we have to downshift, the part where we know we actually retire, right? So what this is this is when at least this is when all of the rays have decided they don't need to do any finer grained checking, is what happens here. Now, there's different ways we might want to do this, and it's difficult to know which one will be better or worse. And we're going to have to probably try them both, because I don't really know which one to do. So, one way we can do it is we can only calculate ray results at the end. So, we won't record ray hits until all rays have gotten down to the appropriate level of granularity for their hit testing. That's one thing we can do. The other thing we can do is anyone who passes the mask without the bound check, anyone who passes the mask records their hit, always. And does not use more granular... You know what? Why am I'm just flapping my gums at you. You have no idea what I'm talking about. Let me draw a diagram. Then everyone knows what I'm talking about. So previously, here's what was happening. I have a sample point, and I'm sampling out through the world, like so. And I've got boxes, right? As I go through the world, I check these boxes. Did I hit this one? No, I didn't. Did I hit this one? No, I didn't. Did I hit this one? Yes, I did. Did I hit this one? Yes, I did, right? And then we only record the earliest. So if I hit this one first, I record it, and then I hit this one and throw it out because it's too far. If I hit this one first, I record it, and then I hit this one and I overwrite it, right? But I'm always going to end up with this one. I'm always going to end up with the closest hit. That's just true, right? However, one thing that we introduced was the fact that the bounding hierarchy has its own record of what the lighting is, generally speaking. And this is a technique to reduce the cost by saying, look, you don't have to traverse the whole hierarchy and get the lighting. If it's too far away, we'll just give you an average of what the boxes in that area tend to give off, lighting-wise, right? So if we were to do that, which is what we're doing now, that means that like this light sample would be recorded instead of this one here on the box that we actually hit. The sort of the parent box would take precedence because we never go down and check the lower boxes. We just use it as the hit. That, once we go multi-threaded, is no longer the case. Once we go multi-threaded, if there are two rays and one or multiple rays, and some of those rays hit this box and other rays don't, then what we will do is if any of those rays would have hit it at a time when we should have traversed it, we will traverse it for all the rays. So if one of the rays really should have used the average, it won't, because we're doing them as a bundle and we choose to traverse that part of the hierarchy or not based on whether anyone needed to, not whether they all needed to, right? So, given that fact, we then have to figure out, well, okay, is that the right thing to do? Should we preserve our old behavior where we recorded the hits and don't traverse for those rays? Or do we allow them to traverse because, hey, we're going to do those checks anyway. It's no extra work for us because we're going to check all these rays as a bundle. So we're going to do the checks and just throw them out if we were to use the hierarchy one. So the question is just, do we want to use the hierarchy one because obviously that could reduce variance since it's using an average from an area instead of using the individual hits, which could vary more? And the other question is, do we really even care? Because how often does that even happen, right? And I'm not sure. It would happen a tremendous amount if we were passing rays that were cast from different starting locations. But since we're passing rays that start from the same starting location, it's a lot less likely. Pretty much what has to happen is a ray has to shoot directly that way, and another ray has to shoot this way. And when this ray hits and this ray hits, that length has to be too far, and this length has to be close enough, right? So this one would go through, and this one wouldn't have gone through, right? But now they both go through. Does that make sense? So I don't know which of those two we want to do. Fortunately, I don't think it's a big deal to do either, really. So I guess we should just test it either way. So, for example, one way we could test it right now, right? We could go ahead and say, all right, we record hits like this, and we just go, anybody who did a hit here does record the hit, something like this, and then we do the recursion after the fact. You know what I'm saying? And it looks like we break in any case, don't we? Right? We had it like this. This break is actually just here. There is no, we're gonna get out of the loop. We're not gonna keep going because when we're checking these axes, we don't need to check any more axes once somebody hits, because if somebody hits, either we will descend, right? Or we will record the hits, I guess. Wait, that's not really true. Is it? Yeah, that's not really true. So that the break statement really needs to go there, I think. Because if we're going to descend from this box, then we definitely don't need to keep checking. But if we're not going to, we don't know which rays have finished and which ones haven't. So I think that is the more correct interpretation. We can break out. There is an early out here, which is if all of them are true, right? So basically, if everyone is true when we're in the hit case, that would be a break, I believe. That's actually valid. I don't know how often that happens. We could count that branch and see whether we even want to bother checking, but I think that's more technically the case. So again, that's the situation here, and the question is, well, all right, do we want to do this effectively up here, which is record all the hits for anyone who was, I guess, not in the close enough bracket of things. So basically, if you were not close enough to descend and you had your mask set, then you would record this hit and let it be primal, right? Ooh, that's not right at all, is it? I thought that was right. Apparently I'm wrong. Close enough to the tier is less of T-max. Well, I guess technically box child count would also have to be in there, right? technically we would have to do this. I don't think that was the problem, though, necessarily. Oh, apparently it was. So I think that is what would actually be required to make the program work the way it was supposed to in the previous version, right? And I just don't know how I feel about it one way or the other. I feel like the added complexity probably isn't worth it. So I think what I'm going to do is I'm going to stick with the previous way for a while anyway. So I think we'll stick with this and we'll fine-tune this a bit more. And then we'll take a look at it later and see if there's other stuff we want to do here. All right. So taking a look here at how this goes, we need to work on this part of our code because this part of the code is garbage. It's complete garbage right now. So we want to figure out a way to make it less garbage. And the way we want to make it less garbage is this is just a loop that takes preferences here. Like it basically takes the values we actually want versus the values we don't based on the mask. So if the mask is set, then what we want to do is take results and replace the ones we have with the new results. If the mask isn't set, we want to leave the old results as they were. So what we want to do is hoist these out one at a time into the result structure that's going to be used as the Raycast result report. So probably what we want to do here is just leave the mask value as it is, because the mask value is the thing that's going to tell you which rays hit and which rays didn't, right? So our hit in the Raycast result, I think that's just one of the things that we need is the mask here. So what we'll do at the outset is in the result, and again, we will now do the thing I started to do the other day, which is to change this from a 0, 1, 2, 3 thing to just being all packed in one. And I don't know if we should make this be a return or not. Probably we should. I'm guessing this should look more like this now. Just to give the compiler the understanding that, you know, the values that are coming into this are irrelevant. You don't have to know what they are, so don't worry about it. And so it can see to inline this routine into the code on the outside and just merge them together. We could do that for it later as well. We could just copy this in. Anyway, here's our Raycast result. And so we're going to start out by setting the hit value to F32 or 0, right? So we just want that to be clear. And we want that to be clear because that's the only thing we actually need to report back in the case of no hits. We don't need to tell it any of this other stuff. So then what we need to do is have these other ones here. They all need to be the same, right? They all need to be done the same way. But what I'm going to do is I'm just going to start again one at a time. So these are all going to be brackets 4 for now. And then we're going to move them out one at a time into actual correct SIMD. So the first thing I want to do is say, all right, let's update the hit value differently. So the result hit value that we're going to, and I'll add that return statement. So the result hit value here is just a thing that needs to get ORed in. So essentially what we're doing is we're filling out the things for which the mask was true. So what we should be able to do is just OR the mask in. Because it started out as all zeros. When we get a lane that comes through as all ones, we just want to slot that in. So we want to just merge those results with what we already have. So that should be the entirety of the update step for the mask. And we definitely don't need to do it inside the loop because it will get all of the lanes that should have been merged. We'll just merge with that one OR operation. We don't have to do it per lane. So that should completely finish that, right? That should be done at that point. And if I go through here and I just double check, I don't think we have like or equals operator or any of that stuff. At least I don't think we do. So I should go ahead and find the times equals sorts of stuff and just make sure we have versions of those. So here's like, you know, plus equals, minus equals, times equals, divide equals. And what I'll do here is I'll just like grab one of these. And then down in here where we're actually doing those binary ops, I'll put those in here. So here's and equals. And here's or equals. And again, we're just using the two-tier state system so that we only have to write the function once and we can get the ops out of it. So make it easier for people to port. So now we just need to do the temporary port work here. Like I said, make these be bracketable like so. Yeah. So here's my raycast function. We're going to do raycast result ray equals raycast and get rid of that. And then when we're looking at the ray here, this subray thing is just going to loop over 4 temporarily, and then it's not going to loop over anything in a minute here. So now when we want to see whether something hit, again, we can cheese this out again by just doing M128U32 here and looking at that sub value to see whether or not the hit is recorded. And then everybody else, oops, we don't need that. We can just use an E, right? Oh, well, I don't really want to do that because that's a floating point value at the moment, so we're going to do it that way. So in here, everything else can just be, you just move the index over to the end, and then we're good. And again, we're not going to leave it that way. That we're just going to do that temporarily as sort of like a stepping stone. So here we are with that code, and that's all fine. And now we have to go ahead and push that down a bit more. So the next thing we can do is target result T-ray here. So we want to be able to hoist this out of the loop. Let's get over here. We want to be able to hoist this out because, again, result T-ray is something we're just keeping for ourselves. So there's no reason to keep doing that by slice because that doesn't even communicate with the outside world, so we don't have to worry about the code on the outside. So what we want to do with result T-ray is we want to select the lanes of T-ray based on the mask. So we want to do a thing where we do like a select function where we take the old version of result T-ray and the new version of T-ray, and we take them based on the mask, right? So we're basically saying, look, this is what it was. This is what the new computation is. If people hit, take the new T values, right? Does that make sense? So there's a couple weirdnesses about this, and I'm not, again, this is why it's a little confusing. So, yeah, no, I think mask is correct. So close enough is the thing that tells us whether the T-ray is less than the T-max. That we don't care about, because that's just a thing that determines whether we go down the traversal or not. So if anyone was true and close enough, we would never get to this part of the code. So we're strictly looking at mask here, is the only thing we're looking at. So I think we're good, right? I think we're good. You know what I just realized too? This isn't quite correct. So close enough, so if someone has to have hit to have been close enough as well, right? So in here, we need to all of this has to be true as well. So close enough technically, let me just back this change out temporarily. Let me show you what I'm talking about. I just noticed this is just a bug. Let me make sure we're okay here. So this is running, it's running okay, right? Like, I mean, it's still producing lighting, but it could have some subtle bugs in it, right? We wouldn't know. We don't have any really thorough test cases yet. To see whether our lighting's working the way we think it is. But if you see here, this close enough value, this is just checking this one conditional. Really, we have to do these together, right? the mask has to be true and this has to be true, because anyone who didn't hit shouldn't participate in the any true close enough check. So this is really more correct, I believe, for a traversal. You know, I don't see much difference there, but I believe that was just a bug, right? Okay, so back to our previously scheduled program. So in here, what I want to do is update T-Ray by doing a select on it, and I want to pass result T-Ray, the mask, and the new T-Ray. So I want to do a select on those. And then that's the exact same thing we'll be doing down here. Excuse me. That same select is what we'll be doing down here as well. So in fact, we can just write these all at once if we want to. You know, we could just say, all right, you know, we need a replicated version of the source index, and we need a replicated version of the box index, and whatever, and we'll go ahead and make that happen, right? So we'll do that in a second, but first, let's just talk about the select and make that happen. So if I compile now, the thing that we're missing is just that call. So in here, we have to implement it. What that's going to do is going to take two of these and the mask value, right? And it's just going to do a simple operation on them, right? It's going to say, okay, if I start with A, I know that I essentially want to take and knock out the lanes of A where the mask has ones, right? So what I want to do is AND it with like the inverse. And it just so happens that that actually exists. As its own operation. So what ends up happening is you do an AND with the not of A, and then you AND it with B. So whatever comes in the first parameter here gets knotted, and then it ANDs with this. So I'll be honest with you, I have no idea why you would call this AND not instead of not AND. Maybe so that you don't confuse it with knotting after you do the entire AND. It's more like AND not A, or I don't know. The name is confusing, but you know, you can see which one it does by looking at the description here. It knots the first parameter and leaves the second one the same. So what we want to do is an and not PS here. And that and not takes the mask as the first parameter because that mask value is the one that needs to be knotted. And then it will take the A value as a thing to AND it with. Similarly, we need to do an AND between the mask without knotting it and B, right? Because that's going to knock out the lanes of B that don't have one set in the mask. And then finally, we will combine them together with our OR operation, and off we go. Right? So there's our select, and it just does exactly what you would think, right? So I think that's all we need to do there. We go and ahead and compile that. There we go. One more. Just need to have that p-value there. Okay. So that's the select function. And in theory now, if we implemented that correctly, we are now no longer doing piecewise ifs on that. We're just doing the lanes as they go, which is good, right? And now what we want to do is we want to do that for the rest of these. So the first thing we have to do is make it so that these can be accessible as U32s, essentially. Like we have to have a way of loading U32s. So what we want to do in here is say, all right, those result values that we're setting here at the outset, we need to have a way of romping in like actual, like values that aren't floats, because we need to be able to return those. And we can't return those as floats, really. We want these box indices and stuff like that to be regular integers. So what we want to do here is just say, all right, we've got our F32 4x for our box index. Oops. And our F32 4x for our box surface index. And then the Ray p-value part, I'm going to leave, and we're going to do that second because that's an actual v3, so we already have a type for that one. So we'll do that one separately. But these two are both going to be done the same way effectively that hit is done, right? So since these are going to be lane confined, really we do need to clear this now because we need to OR things into it, so we can't really have any ones sitting around in there. So as we come through and we OR things into that, no, I'm wrong. We do not need to clear it. We only need to clear that first lane because we're always checking the hit value first. So that's okay. On the outside of the loop, it will never process a lane that doesn't have the hit value set. So that's all right. All right, so our box indices, now what we need to do is when we come through here, we're going to use these box surface index values here in the source index, right? So what we need to do is we want to have a way of updating these two the same way we updated the other one. So we want our result box index, we want that and this. We want these to both be selects that just select the right one. Now, box surface index, I don't remember exactly how that got set. Yeah, I'm going to have to look at this a little more carefully. Because we want to know which one we hit here, and it should be the same for everybody. So it should only depend on the axis index. It should never actually depend on the C index, I don't think. And it doesn't look like it does. Oh, yes, it does, because Ray D. I see. Okay. I'm okay with that. All right, so anyway, this will get selected out of this properly here. So we just need to write the equivalent of these. These select statements will work just fine because these are the same type at that point. So we should be able to just run these directly. The question is whether these values themselves are actually initialized properly up here, and I think that they are. So the only question is how do we get it in there, right? We just need this to actually be initialized this way, but I think we can just initialize it that way without really doing any other work at the moment. So what I can do here is I could just say, all right, the box surface index U32 value, we'll just initialize it this way, and then it just kind of works, right? I think that all just works based off the C index now, and we're pretty much done, right? We could also do this a little bit more cleanly by saying, in here, if you want to access this as something else, you can. So for example, there's a U32 version. Oops. that you can access. So for example, we can just say like that, get it out, and that's probably a nicer way to read that, and it's clearer what's going on when you're pulling or pushing in those values in that way. So that's probably what we would rather do there, I'm guessing. So all right. Right. So source index has never actually been loaded. Source index here is like a non-replicated value. So you can see here we've got just source index. And we need that to be something we can load in here. So we need to replicate this value across. So what we need to do is we need to pass this in. You know, we need to do something like that, where we can create one of these out of an integer value. And it's going to have to do that load that we were doing before. So when we create that mask, right, you can see this set1 PS happening here. This is really exactly what we want to do. So we want this to happen. You know, we don't actually have to do it like that, I guess, but that's what we want to do in our load. So where we're doing our F32 4x call here, we just want to make an equivalent call. And instead of having it be a mass value, it's just whatever it actually is. So then we have the result. The result P equals the casted value, and then we return it. That allows us to load up that in and do our mask operation on it. So again, that's just replicating that value out so that we can use it. So now we need to be able to pull those out. Fortunately, we just added a nice way to do that, so we can just do it like this. And then I think we're done. And now that loop, of course, we're not going to get any faster even if this loop was causing us problems, because the loop is still there, right? Oop, that doesn't look good. So I thought we had done everything exactly the way we were doing it before, but that may not be true. Like, I don't see anything particularly different happening here. What did go wrong? So the select call appeared to be working properly for everybody else. We select the box index after that. Where is our, you know, our hit is checking here. We won't call this unless this comes back as true. So I would have thought we would have been okay there. Let me take a look at what happened. So our box index is definitely completely nuts, right? Let's take a look at what our values are. So here's our array. So here's our hit values. Hit, not hit, not hit, hit. Here's our boxed indices. Completely ludicrous. Yeah. So it looks like the select is going backwards there. Am I wrong about that? We want to select from this to that based on the mask. Did I not write it that way? Did I somehow write it backwards or something like this? Which would be pretty terrible if I did. So we are masking the not of the mask with A, and we're ORing with it no. So that looks right. Let me step through that code. I'm not sure I don't immediately see the reason, so I feel like it's just safer to look. Let me turn off multi-threading again. So that. So let's take a look. Here's our mask. This is the thing that told us what hit. So 1 hit, 0, 2, and 3 did not. And let's just take a quick look to see whether we think that's actually right. So here's our T-ray value that we computed. Oops, the wrong thing there. So in here we've got, 19, 5, 4, so negative 14 obviously didn't hit. Whether 19 or 7 hit, I don't know, but I guess we could look at our bounds check. Here's our X's and Y's. And yeah, I could believe that. These two are pretty close, right? Yep. So this is the only one that passed the bounds check. So that does look about right. It's not ridiculous. That mask seems plausible to me. So let's see what happens. Here's our result T-ray. The box child count here is 2. And I guess close enough did not trigger. So why didn't close enough trigger? What is the result T-ray here? Oops. I'm sorry, what is the T-ray? So that seems wrong, doesn't it? Because oh no, it's right, because it's 5 and this is 6. So no, we shouldn't traverse. That's correct. So this did it right. That makes sense. So we're going to go ahead and do our select here. And we should select 592 into the result T-ray. Yeah, and we did. So then we should mask in the hit. Right here. And we did. Then we should select in a box index. This is just garbage, right? Because we don't need to initialize it except in this slot. So this slot should now get a valid 534. Oh. Oh boy. Oh boy. It's get that on there. Okay, so I don't know why it would surprise me that I can't get correct values out of something when I don't ask it to actually write the value back. You know what I'm saying? Yeah. Suffice to say, I expect better results this time. Yeah. All right. I wonder if we should just have a thing, by the way. Well, no. You know what? I'm not going to do it now. All right. So back to the normal speed. Here is the same thing running, but now with selection there. So the selection has only one piece that's not working now. And that's this right here. So what we'd like to do is we'd like to get rid of that as well now. Now, to do that, we really don't have to do anything other than what we did here. The problem is we don't actually have what we did here, right? We want to be able to call the same thing. We want to be able to call a select function that'll just select the appropriate parts of the mask that pick the ray P4x instead of the ray P here, and not do any of that stuff. So we'd like to be able to do that. And we would like to be able to do it the exact same way. Fortunately, we should be able to do it by literally just replicating the select function, but using the 4x version instead. Right? So if we come down here and we say, okay, we want to have a v3 that's going to get masked by a scalar mask, though. So we don't, notice this one does not become a v3. Because we want to mask every dimension of A and every dimension in B by the same mask. So we don't have a different mask for X, Y, and Z. We have the same mask for X, Y, and Z. So the result function, the result value here, is just to distribute that mask operation over all of them. Like so. So that should do the same select, right, in either case. Now I just need to come down here and make this actually be a 4x. Okay. Oops. So now I believe we have the fully functioning version, which doesn't do any weird looping through the scalars on the inside of the raycast, but it definitely does do weird looping of the scalars on the outside of the raycast. So that's definitely something we could start to address as well. Now, of course, we don't really know where the time is getting spent necessarily because we can't sub-profile it here. So we may need to gather some information to find out what we can do at this point in terms of optimizing that, right? Meaning we don't really know how much this is costing us versus this. And one of the problems is we call this enough times that it becomes kind of costly to profile it at all, right? But if we look here, so, it's not nothing, but most of our time is definitely spent in there. Now, another thing that I'm not sure about is how much the startup cost is. So, another thing I could do is let's just take a look. I'm assuming the startup cost is negligible. I really just want to time this block. I mean, this can't really be very much time. I don't know why I'm bothering. So let's suppose we time this block, which I have named Real Fruit Flavor, just to let you know that it's made with all natural ingredients. And so yeah, that startup cost is not particularly high, right? So this part could be optimized quite a bit, but I don't know that we really care, if that makes sense. So now we're down to just looking at what is a completely SIMD routine here, I believe. And yeah. I don't think there's anything particularly odd going on there. So what I would point out, however, is that we're still not nearly as fast as we probably should be, even with just that one routine. And the reason for that is we're not sampling the hemisphere in a smart way. So what we actually want to do here is do this slightly differently. What we want to do is have our sample hemisphere function also be SIMD, and we want it to produce 4 rays that go in the same direction. So this function, rather than doing this, needs to produce 4 rays that all go roughly the same direction. So they'd start with a random bilateral set that goes one direction or something, and then they'll perturb that, right, a number of times with small perturbations, so we know they all cast relatively coherently in the same direction. So if we take a look at how that would happen, what we would want to do here is say, okay, sample hemisphere, we can already see, if we take a look at sample hemisphere, you can see how it produces a sample D that's 4 wide here. And then it gets loaded like this. So what we can do is we can say, also, I don't know why this is getting produced every time. It's the same, right? It's up, that doesn't vary. So what we want to do is make this be actually produced directly. So we want sample hemisphere to be something that just directly produces a V34X, and then we just get rid of this. And that will generate like essentially a ray bundle that we know goes in a reasonable direction away. So if I pull that down here, so we can look at it, what we want to do is take this and change it into something that behaves that way. So in order to produce this V34X, I guess I'll start off with doing something pretty basic. I'll keep the load as it was. Something like this. And then I'll just say these, and then we'll flatten it down in a second here. So what I want to do is this process is probably fine for each one. In fact, you know what? Let me just do this as a loop for now. And I suppose actually I can just, no. So what I want to do is I want to go through and produce each of these. I'm going to do this by having a basis that is a random bilateral that I pick up here. I'm going to normalize that. And I'm going to normalize it again. That's not really what I want to do. I would rather not have to normalize the first one. I'd rather normalize it at the end. But I'm not sure if I can really guarantee, because if I don't know the length of this, I can't guarantee that I'll be close by on the next one. So it's a little bit difficult there. So what I want to do here is I want to take the basis and add it to this other vector. And I want to make this perturbation relatively small, right? So 0.1 or 0.2 perturbation. And then I will record that. So there we go. Now, in theory, we should be casting rays that are semi-coherent, and you know they can traverse similar parts of the hierarchy, in theory anyway. Now, we probably want to draw this at some point to guarantee that we actually are, because we don't actually know if we are. But we can see, we can see that this is, well, I don't want to stand close to the stairs. Okay. So we can see this is what, like 22-ish on the clock. And we should be able to see a difference, I would think. If we swap to just doing a completely random bilateral here, right? So if we were to say instead that we just use a complete randomization, we should be able to see some difference here, at least in theory, in performance, but I don't actually know that we will. Yeah, you can see that. So you can see here that we're getting like about 30, right? Something like that, 28, 29 or so. If I change it to be more coherent, that number drops down quite a bit, actually. It takes about 6 milliseconds less, 5 to 6 milliseconds less to do. And again, the reason for that is just the number of box checks that have to happen at that point is pretty substantial. Because when we cast rays in opposite directions, they'll check everything in the whole hierarchy, right? Because this one, if two rays go in opposite directions of each other, then we'll have to check all the hierarchy on that side and all the hierarchy on this side, rather than only checking some of the hierarchy on one of the sides if they all went that way. That's what. So when you bundle rays together, you only really get performance out of your spatial hierarchy if those rays are somewhat semi-coherent. If they're not coherent, then you kind of lose all the benefit that you were trying to get out of it, right? So now we're obviously in better shape with our lighting. It's running much more nicely than it was, but it's still not probably fast enough, right? So we're not quite there yet in terms of cycle count, right? We're not quite there yet to what I think we could probably say was reasonable to do at the moment. Now, if we improved our sampling, like maybe we are, I don't know, because the loop, the number of rays here is, if you could somehow drop it down by a dramatic amount, we would get dramatically faster, right? So depending on how our or maybe not. Ooh, that's very interesting data. So that floor is not as high as I would have thought it to be. That's pretty interesting. So yeah, I mean, maybe that is sort of an argument for cleaning up the code around this as well. I'm not sure. We could certainly do that. I mean, there's not a lot of reason not to at this point. Let's go through this, though, one more time and just finish up what we were doing here. So the first thing I want to do is I'm going to get rid of the 4x's on things because now everything is done 4 wide, so we don't have to call something 4x, right? So if anything in here still has a 4x on it, I'm just going to get rid of it. Looks like we mostly didn't, but this one, for example, does. Just getting rid of these here. Oh. So that all looks fine. And I may just go ahead and reinstate this too because it seems like a good idea. So this ray d positive value here, I feel like we could just do well, I'm not sure. I feel like we could just do this in SIMD now, because why not, right? So if we take a look at this, right, this is just a select between two constants like positive and negative 1, right? So really, you know, we could just have some constants here and just do this thing entirely wide as well. Seems worth doing. Also, we could get rid of this loop too. If we wanted to, because we could set the number of children and have it be a known amount, you know? So that could be a fixed loop. I don't know if the compiler is smart enough to unroll the axis index bit here. I also think the way we wrote this down here is not really necessary. So since the close enough part had to be masked already, this is really not necessary. This can come down here. So basically this can look essentially the same as it used to. So yeah. Where do we go from here? That's the question. And I don't really know the answer. One thing I would like to do is take a look at what it did here. So I might want to just say, let's step in here and see. Okay. So it didn't unroll the loop. It did not unroll the loop. I'm just looking at the assembly here and seeing what I think. Because it looks like it goes ahead and does this jump and redoes the code right here, right? So some of these also, I don't know if unaligned moves will hurt us at all there. You know, some of these things we can force the alignment of. And I'm not sure what we want to do about that exactly. You know, but mostly it seems reasonable, right? I mean, so I'm not, yeah, I don't really see much to do here that's, yeah, it all seems pretty reasonable. I mean, one thing that's true, I guess I don't really know, is should we try to simplify the loop for the compiler a little bit? You know, and I don't know. Because, like, you know, looking at the speed of the routine and just wondering, like, do we want to do stuff like just say, look, you can always do this. You know, you don't have to You don't have to do these. You know? Those are early out conditions, but if they make it worse for you, you know, don't do them. And I don't know, right? It doesn't look like there's a particularly big difference between those two. But, like, one thing you could say is it looks like they are kind of superfluous, right? Like, so those are not maybe necessary in the first place. So we can kind of simplify that a little bit. We could even get rid of this one as well. So, you know, a lot of these if statements aren't really necessary. So you can see that that one does make a difference. So having that branch be tested is good. This is, I guess, enough work, right? That if you early out on it, you get a win. Get a good win there. But, you know, maybe these aren't. And we might want to check to make sure that's true. Like, we might have to measure it really carefully to see if that's true. Because we're not really testing this very scientifically here. But it looks like, for example, these are just not necessary. Because maybe the number of instructions that are done here just isn't significant compared to the overhead of doing, like, the move mask and stuff like that. So, you know, there's that. Oops. So the ray value here that we're selecting also this is not necessary to do every time. So one other thing we might want to consider is just moving this out. So for example, this value here, because we kind of did this before, right? We can just say, like, all right, just compute this. Based on the delta value that we do outside, right? So we could avoid doing the select on that, which might be nice, by saying, all right, compute the delta by taking the result oops, that's not it. Result T-ray, and then just compute it here. So, you know, go ahead and oops. Right, go ahead and produce that hit value on the outside so that you don't have to do it every time. You know, that's probably a little bit of a win, probably not significant, but it's a little bit of something maybe, you know. It's also something that we could just do outside, right? It doesn't have to be done here at all. It can be done in the returning code, and because we don't really have to update that value. So, you know, out here in this, when we get the stuff back, we could do something more like that. In fact, we don't even need to do the select, right? The select is superfluous. We can just do that. And then go back to doing what we used to do, which is store the T-ray in the actual thing that we return. You know? So then we've got the ray origin, and we've got the ray direction, which is this. And that should produce the landing point properly for us. on the outside. So then really the result T-ray just becomes an actual thing. And off we go. And that doesn't really need to be called T-ray anymore. It could just be called T, but whatever. So yeah, so we can, again, we can just kind of fuss with that a little bit, do those computations on the outside. They don't really seem to help or hurt us much, though. They seem to be kind of largely irrelevant. So it's probably not really worth looking at that much, but that is that, right? So, and this, of course, we still don't really know if we care about it or not. Yeah, it seems like we're pretty much always up as these guys jump around. We probably want to produce some kind of a lighting test if we're going to optimize this further, where we can produce a reliable, like, you know, environment where there isn't anything moving. So, you know, if we were to do that, I guess I can take like the snake and not add the snake, then nothing is moving. So, you know, the speed of the computation is not dependent on anything, because no box values are changing. So, so a couple things here. So if we wanted to, it looks like we could probably do this code more cleanly as well. You know, we could do this stuff in SIMD if we wanted to. Let me get rid of these. And in fact, there's a lot of stuff here that we could start to improve. It's kind of hard to say, but you know, just looking at it, I do think quite a bit of this stuff we could make a lot better than it is, right? So I don't know how much this is affecting it currently, and I don't know. So, you know, we could first of all pull sample hemisphere in here. We could make this loop just be completely welded together as well. And I don't know to what degree we want to do that, but, you know, we certainly could. So, for example, if we took sample hemisphere and we just brought that directly in fact, what I could do is finalize this sample hemisphere so that sample hemisphere is properly SIMD as well. Weld that in here, drop the raycast in, and then clean this up. And the whole thing could run in SIMD. I just don't know if it, like, based on what we're seeing profile-wise, I don't know that that really helps us all that much. But, you know, we'll see. I want to take accumulate sample and move that down for starters, I think, because I never really liked it being outside anyway. We only did it that way because we didn't previously integrate skylight sampling in, but we do now. So I'd rather have a way of saying, okay, let's actually make this do something reasonable. So here's accumulate sample, and it's passing, you know, sample point index here for dest sample index. So we can just replace desc sample index everywhere we see it. With sample point index, solution is solution. So transfer PPS is the actual light color. So in here where we take the light color, that would be that. And then we have our normal to light. So I can just make that be normal to light. And then this accumulates the sample. Right? So that's just the you know, welding that code in there. And similarly, you know, this again also could be done, you know, just looking at this subray 0 to 4. So I'm just looking at, can this whole thing collapse to SIMD fairly easily? And I think it, you know, pretty easily can. The confusing part is the fact that we've got a different number of surface point index loops to do. And that's why I was saying, like, one thing we might want to do is just say that cubes always have a fixed number, because that would help us as well in terms of getting less indirection happening in that loop. So maybe we just say, hey, look, we're going to fix the number of sample points per side to just be 4 always, or 8 always, or something like this. And I don't know if that's smart or not, because we may want to do something like, well, it's not always the same number per surface, because we don't want to sample the undersides of things as much as we sample the tops, because you can see the tops but you can't see the undersides, right? So in terms of how the lighting is sampled, it really does seem like we would want to have a different number per surface area. So that's kind of a tough part of it. What are you gonna do to see how we want to proceed on that? So okay, so sample hemisphere. Let's go ahead and SIMDize that while we're at it, just for fun. So in order to do that, what I need to do here is just make it so that we create these all at the same time. So I want to start out by replicating the basis vector. And then I just want to do an add at the end, I guess. Seems like it. I'm not sure that's really the most efficient way to do this. I'm trying to think if there's some smarter thing to do there. I mean, really, I guess we want to just have a normalizer 0 function that works across all of them, which wouldn't be that hard to do. So if you take a look at what normalizer 0 does, and really normalizer 0 is kind of iffy here. We don't really want to do normalizer 0. We always want to have a valid array. We don't ever really want a result of 0. So normalizer 0 is kind of dumb to begin with. And it's there just to prevent us from actually doing a divide by 0, but oh, I'm tired. But it's unclear that we wouldn't rather just check for 0 and then not cast that ray, like replace that ray with a better ray, right? So let's take a look at this. Oops. If I wanted to I could say replicate the basis value out to everything. Right, so we start with the replicated version. And then what we want to do is make a version of this thing right here that just computes the value directly and also does this part directly. So it would say, you know, okay, then result plus equals this, or rather equals. I guess we can do it like this. Right, so we basically take the basis vector, replicate it out to all 4 lanes. And then what we'd want to do is take separate randoms for each of these. I don't actually know why are we off on our number of closures here? 1 closure, 2, yes we are. So the next thing we want to do is be able to take different randoms for each one of these. So we really want something that creates, you know, 4 different random vectors. And then it does the rest SIMD wide, right? But we really do, in fact, what we really would like is something that could actually do a wide random, so that we don't have to keep calling random bilateral every time, right? So we'd really like something that just was a wide random number generator that just generated us 4 packed random floats at the same time, because there's not a lot of reason not to have it do that, right? So really what we like is something more like, oops, F32 4x, or I should say, really what I'd like here is something where we did v3 4x, you know, delta and delta.x equals random f32 4x. You know what I'm saying? What I'd like is something that does this, so that I can generate random values into here and generate them all at once. So I don't have to keep like calling and stuffing in that way, which is, you know, which is annoying. So if I did something like this, you know, we can make this be a temporary thing and eventually replace it with a real one later. Then what I can do is say, okay, do exactly this function that we've got here. Do that. And then do this. And that can all be done wide, right? So we can write an inner product function that operates wide. We can do a normalize function that operates wide, and then the other operations in there we already have. So that would be the wide version of that. I'm going to get rid of the sample table bit probably at the moment. Well, I don't know. We can leave that in there for now, I suppose, in case we want to port that as well. So then really the only part that's a little bit weird is the fact that we do one vector first as the basis. But I'm not sure there's really any other way to do it, because you're going to have to, you want to start with the same value for each of the 4 vectors, so I think that's just how that has to work. So if we were going to expand out on that now, that's not what I wanted. Oh, yes, it is. And probably this can just become random bilateral, and it takes a 4x series. In fact, we could just make such a thing, because this is all we use it for. So it's kind of annoying because one of our things doesn't actually want that. One of our things wants to use it separately. So yeah, I'll have to think about that code a little bit. Maybe there's a way to more cleverly do that so it's SIMDizable. I mean, maybe you just generate them and then, you know, do the normalization by pulling them out of the red. I don't know. It doesn't seem great. To be completely honest with you, but so let's go ahead and pretend we know what we're doing here. And this, for now, will not do any such thing. It will just call the thing 4 times, like just a dumb routine would. No, you know, no actual optimization there. No attempting to make it any better than it was. So we do need the random series to come before the SIMD. And I'm not sure, that must be done in our platform code. Is the SIMD in here? No. Where is the handmade SIMD? Is it in the math code? I don't know where that actually is included. Oh, it's in shared. Now I could actually just put that stuff inside Handmade Random instead. So, you know, maybe that's a better way to do it. I'm not sure. Probably not, but it's hard to say. So here we go. We got a bunch of stuff that's... wait, what? Do we really not have a replicate for the v34x? I thought we did. Oh, it's called 2v34x. Not anymore. So now we need these actual functions. Because we don't actually have them, and then I have to deal with this part. So you know what, based on that too, that sort of tells me that I do really not want to have to deal with pulling this, having pulled this out here. So what I can do is inside Handmade Random, I can make this occur just down here. So now all I really need to do is implement the functions we don't have. So if I go into Handmade SIMD, now I can add these functions that we need. So normalizer 0 is one. And the other one that we need is the inner product. Oops. And so these are going to depend on some stuff as well. They're going to depend on having a square root, so we'll see that in a second. We'll have to add that, but otherwise we should be fine. So what we want to do here for the inner product, this is pretty straightforward. We know all about the inner product. We've done it many, many times. So that's just going to be taking the components of these and multiplying them together, right? So you got a.x times b.x plus a.y times b.y plus a.z times b.z. And then we're just going to return the result. So again, it's exactly the same. So, you know, if we go over and look at the math function, if we take a look at our inner product call here, it's the same call. It's the same code. It's just doing it 4 wide. And if we take a look at normalizer 0, the same thing would be true, except now you can see where this is going to get a little bit squinkier. If we come down in here, where we're returning a v3 4x, you can immediately see where the problem arises. And that is that although we can do this pretty easily, length squared obviously is just exactly the same as it would be. Same exact code. The problem that we're going to have here is this is a conditional, and we don't want conditionals. And there's that square root that I was mentioning before. But it's okay, again, because we know that we can actually turn this into a mask. And then only update based on the mask. Right? So what we're going to do is we're just going to do a select call here from results, mask, and then, you know, the actual normalized value. So what you can see here is we're just going to do take the length, we're going to compute the actual normalized version, and then we're going to do the mask based on, excuse me, we're going to do the mask based on whether or not it passes the conditional, and if it does pass the conditional, then we will use the result, otherwise we won't. So that normalizes all four at once, and only actually updates the ones that weren't too low to use. Now the square root value again is we're gonna have to have a square root because we don't have one right now, so that has to actually get updated. And you can see this is an inverse square root, so we actually have the option of doing an inverse square root, but we don't probably want to. And let me talk about that a little bit here. I think we've covered this before, but it's worth mentioning again. So here's reciprocal square root. That's 1 over the square root. And I'm going to pull up another copy of the Intel Intrinsics guide here, like so. And then I'm going to show you the actual square root. Okay. So what you can see here is that the reciprocal square root is like way faster than the regular square root function. So, you know, even if you're talking about a particularly fast CPU here, it's like 3 times slower to do these than to do the reciprocal, right? So doing a regular square root costs 3 cycles, and doing a reciprocal square root costs only 1. And you already get the reciprocal. So not only do I have to spend the 3 cycles, even on the fastest possible case, but I also have to do a div afterwards to do 1 over, right? And that's another 3 cycles. So I'm talking about 6 cycles worst case, and that's the throughput, not the latency. So best case scenario, I've got other things in the pipeline. It takes me 6 cycles, whereas here it's only going to take me 1 cycle of throughput. So you can see that it really is very beneficial to use reciprocal square root. The problem is it's not right. The reciprocal actually doesn't give you the real reciprocal square root. It gives you an approximation to it, and it tells you the relative error here for the approximation. 1.5 times 2 to the negative 12, right? So the question is, can you use that reliably or not to normalize the value? Or is the thing that you're using going to be wildly inaccurate when you try to normalize it and it turns out that it's not actually normalized, right? So it's hard to say. It's really hard to say. And in a lot of cases, you probably need to be able to determine which one you actually want. In our case, I think I'm going to say we can use an approximation one here. And what I want to do is call this approx normalizer 0. And the reason I'm going to use the approx one is because I feel like in the case that we're using it now, we don't care for a little bit off. Sometimes we would. For this, we don't. For raycasting, we don't care at all. It doesn't even need to be normalized. Our raycast would work whether it was normal or not. So the only case we actually care if it's normalized is actually at the end where we're where we're doing the dot product to find out how the lighting fall off works. That's the only place where the error could actually accrue. So I think we're okay using the approximate value here, so that's why I'm doing it that way. So to do an approximate square root, what I need to do is I need to do the divide. Here's the 1 value, and then I want to divide by the approximate square root, or rather multiply by the approximate inverse square root of the length squared, and that's, you know, the whole shebang. So that's really all we're talking about here. So the only thing we need is that approximate inverse square root value, because we don't actually have one of those for our 4 wide. We don't actually have one of those for anything, really. We've never written that before. But to do an approximate inverse square root, again, it's very simple because it's already in there. It's already in the chip, so we don't do any work. We just ask the chip to do it for us, right? So looking back here, you got r squared ps. All we do is pass in the value, and out it pops. Oops. So that's really all we're talking about here, right? Pretty basic. Now, the thing is, I believe... I don't remember if there's a refinement call in here. I don't think there is. I think you just refine it yourself if you want to. So I don't remember if there's a refinement call, but let me explain what that is, and then I'll explain why I don't think we care in this particular instance. So sometimes what happens is if you do approximate computations, those approximate computations can be followed by fix-up, which will improve their accuracy. And sometimes you want to do it if you care about getting that little extra. Sometimes it's cheap enough that you just do it. I don't think there's any refinement to be done here. I think you can do refinement yourself, but I don't know if there's any point to it. So I'm just going to skip that part of it, and we'll just use the approximate inverse square root here anyway. All right, so taking a look here, what we want to do is push this. That's a scalar. So we want to smush those scalars first and then multiply by the vector. Cannot convert to, that's a good point. And there we go. All right, so taking a look here, we don't have this anymore. We only have the approx normalizer 0. And then the inner product here is result and n. N is not load opt up, so we need that to be bigger, right? We need that to be replicated, so we can do the wide product. Oops. Like so. And we need the inner product here, which is going to produce a float again to this is just 0. And off we go. So again, this is also a mask situation. So this is just going to be a mask, and then we need to select based on the mask. And now we're wide. So yeah, in theory, if we didn't mess anything up, that's the sample hemisphere function, right? And it's pretty straightforward. And now it's operating in SIMD instead of what it was doing before, which is not operating in SIMD. Again, we want to go through this after we're kind of done with it and do some checking to make sure that we're still doing reasonable stuff everywhere. We never really checked it in the first place, so we would like to do that eventually. So the last thing I'll do is I'll just drop this down into, and you know what, I don't really care about this anymore. We'll put the sample table back in, we'll write it new because it would have to be new anyway. So I'm going to get rid of the sample hemisphere function here, and I'm just going to go ahead and drop that in so that we can see it in place, which is right here. And what I'd like to do there is, yeah, just go ahead and take this value here. Like so, and so now we've got these here. We're not using the x-axis and the y-axis at the moment. We're only using the sample point n. So what I can do is I can just load that up here and leave that be. It's never going to change. It doesn't change in the loop because the sample point is the sample point. It's normal, is never different. So when we actually do this here, check here, we can do sample point n, like so. And I think that's it. I agree. And so this delta and that delta are not the same delta anymore. I can actually get rid of this anyway. Just put it down there. And so that seems fine. And again, so now we're just like further welding that routine. And I think we're now in pretty good shape SIMD-wise, right? So we're now running our lighting at actually well above 30 frames a second. So that's pretty nice, right? Whereas before we were running it at maybe 15 frames a second. And we're actually closing in on 60 frames a second lighting CPU side, right? Not using any GPU for that at all. So I think, you know, that this could work out. You know, maybe we'll just leave the lighting on the CPU and just leave it that way for the foreseeable future. And if someday we want to convert it to GPU afterwards, because, you know, if we have something that works, we can develop the rest of the game with it, right? And then we can always come back and decide to do a GPU version later if we decide that that's what we needed, right? So I think we're okay with that. I'm going to go ahead and go to Q&A. Yeah, if anyone has any questions about what we did, off we go. And I saw someone asking about how much CPU it takes to do. So if we take a look here at the CPU cost, here's how much CPU we're taking. And you can see if we go to the profile, So actually the frame display is taking quite a bit of time there. So actually, yeah. You can see we finished, you know, the lighting gets finished actually pretty quick. It doesn't even, yeah, it's not even pushing that limit yet. So we're within earshot of 16, I think, actually, just looking at this. We need a frame rate counter we need to put in a frame rate counter that will work if we turn off profiling and stuff like that, right? Because for all I know, we actually are running at 60 frames a second if we turn off all the rest of this stuff. So if we went, you know, full bore, I don't know how much overhead there is at the moment with other stuff. because we don't have a, like, once we turn everything off, we don't get a frame rate counter. We need like a low overhead, very simplistic frame rate counter. So we just know what our frame rate is when we're in full bore mode. Like a frame rate counter that could ship with the game so users could check their frame rate. That kind of a frame rate counter, not one that relies on our debug system doing all kinds of weird stuff. Excuse me. But anyway, yeah, like, you know, we definitely need to reduce a little more flicker. But it's pretty cool. This is getting pretty cool, in my opinion. And the other thing I guess we should remember is that the flicker is worse. The worst flicker will be when there's the least lights in the scene. So a single light moving around illuminating the whole scene is actually the worst possible case for flicker. So, you know, there's that. What version control system do you use? For this, the version control system is actually GitHub, because people who pre-order the game get like access to the GitHub. People wanted that, so it checks into GitHub every day after we finish. But that's only for this project. On my own personal projects, I have a custom version control system that I wrote, and that's what I use. Obviously, I don't use GitHub. My development machines are not connected to the internet, so they wouldn't be using GitHub. Neil asked a question. Well, it wasn't really a question. It was a request. He asked if we could look at the profile, and yes, we can. I guess if we don't have Handmade slow on, we won't get a debug, so I'll have to turn Handmade slow on as well, will I? Oh, no, I won't. So, okay, I can take a look at this using that. So if I put the thread view on, what you want to know was if we drop the ray count down, what happens here profile-wise, thread-wise. So, you know, here's what it looks like. Let me go ahead and inside the Lightning code, drop the ray count down to 4. We got it. That's annoying. So dropping the ray count down to 4. So yeah, I think it's just we're just missing the 16 frames a second there, I guess, is what's happening. So the frame, like, you know, if we turn VSync off, I guess is what I'm saying. So let's suppose we turn VSync off. I suppose we would see what would happen there. So here's the swap interval call. If I was to change that to 0 so that we just lets it swap immediately, you know, that would, I suppose, tell us what was going on there. I don't know, maybe it wouldn't. Yeah, that's just kind of weird. So it looks like... I don't know why that's not showing all of our frames there. That's weird. I'm not sure why... I'm not sure why that's happening. It looks like just the rendering actually takes that time. I mean, That's just the slowness of sampling the lighting, I guess. Yeah, I mean, look. So we're running at under 16 milliseconds. If we just don't draw the world, we're running at the lighting just fine, right? So if you take a look at that profile, we're A-okay. So it looks like the problem comes when you actually need to render, when it's actually sampling the lighting, that pixel shader, I guess, is just too slow. Which is fine, because we can speed that thing up. That's not going to be a huge issue. To make that thing faster. There's tons of stuff we can do for that. So yeah, I don't know. Like, if we want to check out the actual slowness per ray, I guess you just crank the ray count up and get rid of the drawing. So then we can actually see, that's should be dominated entirely, by the light computation time. So yeah. Next, you cast the input value in the U34X loader to a float. Why is that? That's just C syntax for forcing it not to adulter the value. So if you take a look at what's going on here, you're passing in a U32, but there is no set call that sets a SIMD register to a U32. This is purely because Intel's intrinsics are kind of dumb. The processor doesn't care. The processor's just going to load bits in. So the unfortunate part is Intel just didn't decide to do the intrinsics right. So they have set, and you can see the set of calls here that you use. And what you'll notice is for things that are going to use an M128, why do I not see the PS calls here? Oh. Where are the set calls? Oh, there we go. I didn't have SSE1 checked. That's all. So if you look at all the values that are, if you look at all the things that are available here, right, you can see the options that you have. And what you'll notice is that if you look at the intrinsics you've got for producing an M128, which is the floating point type, in the C compiler, you can see that you've got like set R, which sets them in the reverse order. You've got set 1, which sets them in the forward order, and so on. But they all take floats. Now, there is a call which takes integers, so if you wanted to load an int, you could. Here it is, right? Set1 EPI 32. Now, that's a call we'd like to make, pass an integer. The unfortunate part is it returns a different type. It returns an M128i. So in order to actually put that into our M128, these are the same concept to the CPU. They're both just the register, but what ends up happening is we would have to call a cast instruction. So we then need to do a cast to convert our I, so you can see here, convert our I value to a regular value, it's purely C-type nonsense, right? So what I did instead is I just said, hey, look, pretend the bits I'm giving you are float. They're not, but pretend they are, Mr. Compiler, and please load them. And then it will. So that's what this is doing. It's just, basically telling it to reinterpret this. If you use like C++ style casting, you can use an actual cast declaration for that, like reinterpret cast and static cast, those kind, if you use those. But I don't care for those because they just introduce complexity that doesn't actually do anything. How does the mask replace an if in the SIMD instructions? So it replaces an if like this. We've gone over this before, so you can actually search for this in the Handmade Hero episode archive if you want, but it's pretty quick to explain, so I'll just tell you again. So the way that SIMD works, and the reason I didn't go over this for this is because we've gone over it multiple times before, so you can go back and read this if you want. So we've got lane 0, lane 1, lane 2, and lane 3. Okay? So normally you have something like a float, which we call an F32 in Handmade Hero, that's 32 bits. And this represents one value, like 2.3 F, right, or something. Well, in a SIMD register, we've got 4 of them. So we've got 4 floating point values, each of them at 32 bits. Right, so we've got 32, 32, 32, 32. So in toto, we have 128 bits in one register that packs 4 floats together. 4.3, 2.1, 9.0, 11.7, I don't know. Right, so we've just got some floats in here. These are floating point values. Now, what happens inside a normal processing operation when we were using conditional branches is we say something like, okay, x equals 2.3 f, but if something happens, right, then, x equals 4.7 instead. So that would be fine, but once we go SIMD, we can't do a conditional branch because what this was doing in the code was it was literally skipping this instruction. It was telling the processor to just jump right over it. Well, since this if conditional will evaluate potentially differently for all 4 lanes, we can't skip the assignment, because if we did, the ones that were true wouldn't happen, and the ones that were false, so all the lanes that were false would end up at the right values, while all the lanes that were true would end up at the wrong values at the end. So what we do instead is we produce a mask that is the result of this conditional slotted into lanes. And what that mask has is it just has exactly the same thing, 128 bits. And it just has 1s for all the true values and 0s for all of the false values, right? So if the conditional would have evaluated to true on a particular lane, that lane gets 1s, all 1s, and if the conditional would have evaluated to false, it gets all 0s. And hey, this instruction set was designed together, so as you would expect, the conditional instructions in SSE actually produce this exact mask. So we don't have to do any work to make it. When we just do a comp less than or whatever, we get a mask out of it. So then all we have to do is just bitwise operations to produce the result we wanted. We want a result here, right? And we want to take 2 things, like let's say we were doing exactly this, right? So we want to take 2 things where we had some other values here. We've got 4.7 that was supposed to be set. So we have an input value, and we have like our new value here, 4.7, 4.7, right? And all we're going to do is we're just going to do an operation, a bitwise operation, to produce a result so that we get this value in the case of the false and this value in the case of the true. Well, what would that be? It's pretty straightforward, right? All we have to do is OR these 2 things together after ANDing each respective one with the mask value in the correct way. So to preserve values in the input, we would want to AND with the opposite of the mask. Because if the mask was 1, we want to take the new value. So we want to knock out all of the values here where there are 1s in the mask. So that's why we did an AND not on the input. on the first value. We call this value A in that routine. For the new value, we just want to AND with the mask directly, because wherever it's zeros, we want to knock out. Wherever it's ones, we want to keep. So we just do a regular AND with the mask for the new. Then we OR those two together, and only one of them has survived, because one got an and one got an and not. So only one of these two values didn't get cleared to 0. So then we just OR the bits together, and we get whichever one of them wasn't in the result. And that happens for every lane separately, right? So that's how we do a conditional. Essentially what we do is we run both sets of code, the if and the else, right? We run both sets of code, and we just keep whichever part we want based on the mask value. And like I said, we went over this in a lot more detail back when we talked about SIMD originally. So if you want kind of a slower walkthrough, you can get it. But the idea is just to use that mask. So you just say, you know, the result always is equal to A and not mask, or B and mask. Right? Now this is a fundamental SIMD operation, and it's usually called select. At least that's what I usually call it. And you may ask, why isn't that just in there? The answer is because it's a ternary operation. It requires an A, a B, and a mask. And SSC doesn't have ternary operations, really. So what ended up happening was it just wasn't in here at that. But it does eventually come in later. Let's see here. I don't remember where it is. I don't even remember what it's called. I never use it because it was like SSE4 or something, which I don't use. Soon, I think the installed base will basically always have it, so I may start using it. But I'm sorry, I'm blanking on the name of it, but it's there. It's there somewhere. What's it called? I thought it was there somewhere. Here's someone suggesting a better one, which is an XOR of the and the XOR. I don't know if that's actually true, but that's not what I want to know. I just want to know where that SSE select was. I think Fabian... Wait, I totally spelled his name wrong there. Had it on his reference. I seem to remember it being in here. I'm just trying to think of some code that I've seen that had it in there, so I could look. I feel like this had it in there. Somewhere. I must be wrong about that. Blend. Blend. That's what they called it. That's what I'm thinking of. Or not. How come I can't get that? pblend VB, it's in there. Oh, because bit manipulation was set. Oops. Sorry about that. So yeah, so as you can see, the subset we were targeting doesn't have it. SSE3 doesn't have it. Neither does that. But once you get up to SSE4, you've got blend instructions. So you've got blend V, and that's the phrase I couldn't think of as blend. I don't think of it as blend. I think of it as select, but you know, whatever. You know, call it whatever you want. So this instruction, which I never really get to use, but which does what you want, this is actually the instruction in question. You know, that's how it works. And I'm not sure exactly how it knows what the mask value is, because true ternary instructions, I thought, were only added in AVX 512. So I don't actually know how pblend VB knows this. Like I said, I've never used this instruction. So if we look at the actual Intel architecture manual, this is probably everything. Hello? All right, so if we take a look at the Intel architecture manual, we should be able to find, you know, essentially what that instruction actually does and how it does it. Again, for those of you who may be unfamiliar with this, so instruction set architectures obviously have concepts of how their instructions are laid out. And if you have instructions that generally can take 2 registers, those are binary instructions. If you have instructions that can take 3 registers, those are ternary instructions. And in order to say mask A and select from A and B using mask C, that requires 3 registers, which is ternary. So the question is, how is it doing it? Because I don't think they had true ternary instruction encoding in SSE4. Now, maybe we'll find out that they did, and that will be the answer. But if that's not the answer, then what has to be true is that, like, oh, it's a secret way that it works. Like, you always have to have the mask stored in XMM0. And so we always use that register as a mask, isn't it, right? So I'm just curious to find out. That's why I'm looking this up. Yeah, that's not going to happen. All right. So here's the Intel architecture manual. We know we are looking for the documentation on pblend V. And And so why am I not seeing any highlights? Forget it. I'm just going to go look at it directly. So we know it's P, so it's going to be in here. So let's just go grab P blend V. So here's P blend VB. And hey, it looks like I guessed correctly. So the answer is it just knows secretly that XMM0 is the mask. So it's still a binary instruction. It takes XMM1 and XMM2. So you can pick A and B, but the mask has to be stored in register 0, which means that the compiler has like a constraint on where it can output that. So it's register constrained there, where every select operation will be fighting over XMM0 as the place to store the mask, and hopefully that's not a big deal, because usually you're kind of using the mask as you go, and so it won't be a huge deal, but that's how that works. So yeah, there's your answer. I guessed right simply because I kind of knew that they didn't add ternary instructions till later, so I kind of guessed they had to use a fixed register, and so I could have guessed 15 or I could have guessed 0. I guessed 0 because I thought it probably was more likely they'd use 0 than use the bottom than the top, but that was a purely wild guess, so I just got lucky on that one. So there you go. So what you can see here as well, so let's take a look down here. So what you can see is this one starts, so once you get up to AVX, it looks like they actually do have ternaries here. So it looks like maybe you don't have to wait for AVX 512. You can actually have, that looks like a ternary to me, right? XMM 1, 2, 3, and 4. Select byte values from XMM2 and XMM3 using mask specified in XMM4 and store into XMM1. So that's actually a quaternary instruction if that's really the case. I didn't realize they added quaternary instructions. Again, I don't ever get to program these instruction sets. I never get to use AVX or AVX2. Someday soon I will. You'll be able to ship games on AVX soon. I would think. I don't know where we're at on that. So I guess I don't know where to get that data. Oh, here we go. We can see items here. So maybe one of these has it. Here we go. So it looks like, SSC3 is becoming a really safe bet, right? Doesn't look like anyone in recent times was coming on Steam with those. SSC4 looking pretty good, so I could probably start using that blend V instruction and not really worry about it, right? AVX, looking pretty good at 90%, not too bad. I don't know about AVX2 because they're not showing it here. So I'm not sure how to know that one. But AVX is looking kind of good, right? Like, I could imagine saying, all right, let's just go AVX, go 8 wide. Why not, right? If everyone's got it, then there's no reason not to go 8 wide. And that would double our ray count if we went 8 wide, right? So that would be kind of nice too. I'm surprised to see that number that high. I'm a little concerned that maybe that's not very accurate, but who knows? Maybe people are updating their machines. So yeah, it looks like SSC4 is definitely on the table. it's getting down to the noise it looks like there. So I don't know. Just something to think about. And a thank you to Fabian for using that blend instruction, and so we could remember what it was called. Why does the light flicker even when the cube is not moving? It's because of the sampling, right? We're using randomized sampling, so every frame we get different results back from the sampling, right? Could we ship with SC4? Yeah, so we might be able to. You know, maybe we should change those to 8Xs, you know? What can you see in Task Manager's GPU tab? I didn't know there was a GPU tab in Task Manager. When did they add that? Do you mean this column? Or do you mean that, or I don't know if I don't know that I can expand on that. Like, I don't know that, does it have a, oh, I didn't even know it had one of these. That's cool. I mean, they're not much surprising here, right? And I assume that if we just get rid of the rendering, right, you can see that we no longer max out the GPU. So. Do you have any tips on talking with non-programmers about programming related concepts? No, I don't think so. Tbot T, how does your profiler work? Does it hook into the compiler? No, it just times the code using RDTSC. Could we compile one XE with SSE4 that falls back to SSE2 if it's not present on the CPU, or would we need to compile into several XEs? No, we could do that. The way you would do that is you just you have two routines. You have the SC4 one and the SC2 one, and you just at the beginning you patch a pointer that points to the right routine based on your check of the CPU. I don't know what the best way to do that nowadays is. One way to do it would be to just call the SC4 routine. If it doesn't fault, call the SSC2 routine. But I'm not sure if that's really the best way. It might be that you want to check the CPU ID instead. It's hard to say. All right. Let's close up shop for today. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow on the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can play around with it yourself. Let's see. I guess this is it till next week, so we'll be back here next weekend when we will clean up the lighting some more and maybe take a look at some sampling options that we have to reduce the flickering a little bit. And the other thing we should probably do now, because it's about time that we did that since we're running at 30 frames a second at least, is to actually do a little bit of world gen that will use the lighting and just kind of get the whole pipeline going. So we've got kind of a little world setup that's actually, it's big enough and has lighting on the trees and stuff as well. Like, get to the point where we actually are using it for real so we can optimize in the real scenario from here on out. So we'll start that next week. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.